Okay. Oh, thank you all for joining again and inviting me to speak this morning on sustainability. It's obviously a very hot topic in the industry at the moment. So, as Con Natapong was saying, I'm Adam Peacock. I run the building structures practice in Thailand for Oricon and also in Vietnam. I've worked with the business in New Zealand and Australia. Did some time in the Middle East, then Vietnam and Thailand, and I worked on some large-scale projects all around the world. So what is sustainability when we're talking about embodied carbon? It's not all about carbon. Yep.
Adam, can I interrupt you for a second? Perhaps we'd like you to do the slideshow. Click the very lower right button.
Yeah, I thought I was. Ooh,
You did?
Okay. Yeah, sorry, I wasn't. Maybe I was not sharing the right one. Okay. So when we're talking about embodied carbon, it's not all about the carbon, but it sort of is. And by that, there's a number of greenhouse gas emissions, and there's various gases here. So there's carbon dioxides and sulfates and nitrates that all contribute to the global warming potential. But to make it simplified, we basically equate all of those other gases to carbon dioxide equivalent. And so embodied carbon is basically a measure of the kilograms of CO2 E, where E stands for equivalent. And to work out the embodied carbon, it's basically the kilogram or the weight of the materials multiplied by the carbon intensity of those materials. The hard part of that equation is actually working out the carbon intensity. Anyone can work out the volume of those materials that are in a construction project, but the hard part is working out what the carbon intensities are. So a lot of suppliers have EPDs, so environmental product declaration sheets, and they basically outline the carbon intensity of those particular products, and it considers all the way from extraction of raw materials, all the transportation, all the manufacturing, and then basically when it gets to site. But a lot of suppliers don't actually have those EPDs yet. So that is a bit of a challenge here in Asia at present for some suppliers that don't have EPDs. And then also trying to ensure that we're getting consistency in EPDs across the whole industry. So, for example, if one supplier has got an EPD that only considers A1 and another supplier has A1 to A3 modules, which I'll go into in a future slide, there can be complexities there getting comparable results between them, so a like-for-like comparison. And a lot of clients, when they're looking to get sustainable outcomes, they need to have realistic EPDs on their projects. So when we're selecting suppliers, it's important to be able to have those EPDs so that we can actually do the embodied carbon calculations and be able to articulate and provide calculations to our clients to show what the embodied carbon associated with those materials is. So I think that there's a bit of an opportunity here in Thailand at the moment to get consistency and to achieve additional EPDs in the industry. So when we're looking at the life cycle, there's all these stages. There's A1 to A3, which covers the product stage, A4 to A5, which covers the construction stage. Then once it's built, the use stage of the building, so that's B1 to B7, and then at the end of the life during the deconstruction, so the C1 to C4. And then more recently, there's the module D as well, which takes into account more of a circular economy. So it takes into account the reusability of materials or recyclability. Then there's a little bit of jargon here. So cradle to gate is considered the upfront embodied carbon, and it only considers the A1 to A3, so the product stage. Then we've got cradle to grave, which considers the product stage, the construction process stage, as well as the use stage and the end of life stage. And then cradle to cradle considers also that end of life. So after the building's used, say if the building's got a 50-year design life, once it's at the end of life, when it gets deconstructed, can we reuse some of those materials? And the reusability of materials is actually quite difficult as well, because if you can imagine, a designer won't necessarily know what available steel is available from a building that's about to get decommissioned. So there is a bit of work in this space also, There's talk about potentially having material passports for different construction materials. And so, for example, a steel beam might have a material passport that is associated with it, that is tagged, and it might say when the use life by date of the steel is, when it's going to be becoming available in the market, the grade of that steel, and then it can allow designers to be able to incorporate it into future buildings. And then if we're looking at the carbon emissions over the whole of life of a project, initially it's the up till practical completion of the building. So up till it's constructed, and that's the A1 to A3 modules, and that's a big part of embodied carbon. Then if we go to the operational of the building, it's mainly about the operational carbon. So the electricity used for the air conditioning and the heating and cooling, etc. And there's a little bit of embodied carbon associated with repairs and maintenance and reinstatement, but it's largely the operational carbon during that stage. And then there's a little bit of embodied carbon at the end of life as well, when the building gets deconstructed. So there's been a lot of focus on the operational emissions, and there hasn't been a lot of focus on the embodied carbon emissions over the recent years. So there's a big focus now on trying to reduce those embodied carbons, and that's going to be the big challenge moving forward. So why? So the construction industry contributes to approximately 40% of all carbon emissions in the world. It's a huge portion, it's nearly half. And a typical building here, we can say embodied carbon might be slightly less than quarter, depending on the building topology, and it's mainly operational energy. But more recently, there's been a lot of recent research on how to reduce the operational energy, how to make buildings more efficient as far as the MEP systems, etc. And so the embodied carbon becomes a much bigger portion of the overall building carbon, effectively. So there's a big emphasis now on trying to reduce the embodied carbon as well. These are the trends that are expected over the next 20 to 30 years as well. So the orange is the operational carbon. So we're expecting that buildings will become more efficient as far as the MEP systems and the heating and lighting, etc. So that will reduce over time. The embodied carbon is expected to become slightly better, and you can see here that the area of construction is likely to increase in the order of about 20 to 30% of what it currently is. So the emphasis has to be on the embodied carbon to pull this blue component down as well, because by 2050, say, the embodied carbons will be a much bigger component of the overall carbon emissions of the building stock. So why? So in our everyday lives, the average person will emit around about 15 tons of carbon dioxide in a year. So that's commuting, traveling, living basically, traveling to an office, being in an office, living at home, having heating and lighting at home. Whereas an average project might use around 3,000 tons of carbon dioxide. So this is actually the figure of embodied carbon for this 25 King Street. And that building is actually our office building in Brisbane. And it's quite a sustainable building. It's mass timber, and the 3,000 tons is about a 75% reduction from an equivalent steel or concrete building. So equivalent steel or concrete building would be about 12,000 tons of carbon dioxide. So as you can see, though, that what we do in our personal lives is a fraction of what we do in our professional lives, of the buildings that we're designing and what we're involved in. So the focus in our business is to focus on the buildings rather than the personal footprint. We're also in an age of data. So the amount of data is increasing exponentially. We're seeing that with all the Netflix and all the streaming providers, all the cloud storage software, and now more recently with artificial intelligence. And that's expected to be the largest disruptor coming up. So the amount of data needs to exponentially increase. And this data is generally contained in data centers. And data centers are very carbon intensive buildings. They can consume up to 100 times the carbon of a typical commercial building. So they're very heavy. They need big, large, robust structures to house them. They generate a lot of heat. They need a lot of cooling. And the shelf life of a lot of the components in a data center might only be about 3 to 5 years, and then it typically ends up in scrap. So they're very carbon intensive buildings. So if we understand that here in Thailand, that we're about to head into a wave where there's potentially a lot more data center activity. And given how carbon intensive they are, there's a huge opportunity for the industry to make for more sustainable buildings and really make an impact on the environment. So why? When it comes to clients trying to persuade to make sustainable choices for buildings, it can be quite difficult at times. So the approach obviously needs to be sound. And so doing the right thing won't necessarily be enough. Okay, so there needs, most clients, when you say you present a sustainable solution, they'll say, where's the return on investment? Right? They're a business, they want to see some return on investment. So one benefit of achieving more sustainable buildings is you can get LEED credits. So by achieving a 10% reduction in embodied carbon, you can get additional LEED credits. There's a whole category that's associated to embodied carbon. This here is also quite prevalent in places like Singapore, and it might come to Thailand, the cost of carbon offsets. So as you can see on the graph in the bottom right, the cost of carbon offsets has actually increased significantly over the years, and it's expected to increase into the future as well. So if you achieve a more environmentally friendly building, then you'd have to pay less on offsets. So there's a financial incentive there. Some locations like Singapore and Hong Kong offer increased sellable GFA for buildings that achieve a higher sustainable outcome. And some financial institutes such as UOB offer financial incentives like lower interest rates, etc., for more sustainable buildings as well. So when all this starts to get factored in, it can actually come out cost neutral overall, even though the capex may be slightly higher to get a more sustainable building to begin with. And the rally is it's going to end up being mandatory. It's going to be put into codes and standards in places like New Zealand and Australia. They're already producing drafts of what these standards will look like. And right up there with doing strength and serviceability calculations, structural engineers will have to do embodied carbon calculations as well and meet a certain threshold to get building consent. Currently, the sustainability isn't a must. It's more a desire. And buildings can get built by just doing strength and deflection calculations, etc. But in the future, it will be part of the codes, and it will need to be adhered to in order to get construction permits and the like. There is some limitations to top-down approaches in some countries. So a lot of those, say the increase in sellable GFA, and some of those financial incentives aren't available in some countries yet. So I believe it needs to come from both bottom up and top down approaches. So bottom up, consultants, we can be specifying more environmentally friendly materials. Suppliers can be developing more environmentally friendly products, but also from top down. So if the government has those mandatory requirements in place whereby developers can get tax incentives or increases in sellable GFA, etc., then all of a sudden it becomes much more financially viable to achieve more sustainable outcomes. So I think that's very important as well to achieve this outcome. So the how. This is from the iStruct-E, and it's basically the hierarchy. So obviously using less stuff will be more environmentally friendly, specifying lower carbon materials, and then lastly, offsets. So within that, use less stuff, obviously build nothing, but that's not always going to be possible. Then building less, so can we renovate or refurbish an existing facility? Building clever, building efficiently, and then also trying to minimize waste. So effectively designing less, can we achieve the same outcome without building smarter? So I'll go into a few examples about smart layouts and smart grids, making sure we've got the right structural systems, etc. Building efficiently, so making sure that our structural members are highly utilised, and trying to standardise where we can, and then trying to minimise waste. So using prefabrication or modular construction to try and minimise waste. In New Zealand, there was a seminar recently, and it was a staggering amount. It was around about 40% of the construction materials on a site were turned into waste. So yeah, I think moving more towards modular and prefabrication can certainly help reduce the waste, as well as a lot of these projects, speed to market is a key driving factor. So I think modular and prefabrication can play a key role in that as well. And then the specifying low carbon materials, so that can obviously be part of the structural specification for steel or concrete or timber or whatever the material may be. And then offsets is basically just there as a very last resort if needed. And then so this is an example going from a 6.5 metre grid, a 7.5 metre grid, and a 9 metre grid. We were able to achieve significant reductions in embodied carbon. So you can see there the 6.5 metre grid is much more efficient. It's got around about 200, whereas the 9 metre grid's around about 340. So it's nearly half. Then the other, so using more efficient systems. So that example down on the bottom left, there's a typical PT slab with PT band beams compared to a reinforced concrete waffle slab. And that had huge reductions. That was also around about a 50% reduction in embodied carbon using just changing the floor type. When we're looking at the facades, so the facades play a very important role. The facades behind the structure, they're the longest living component of a building. And there's not actually a lot of work that's been done historically to try and make facades more environmentally friendly. So I think there's an opportunity there to come up with more lower embodied carbon materials for facade systems. But in general, what we're trying to achieve with the facades is for them to be well shaded to block that solar radiation and the heating inside, well insulated, airtight building envelope, and that will reduce the amount of heating and cooling and the energy used to keep those areas at a nice condition. There is passive house certification that provides basically a framework to achieve this more efficiently, and we've got some case studies on some of our projects in Australia where we've achieved this as well. And this is just an example. This is the SAMRI building. It's a medical research facility in Adelaide, and it's nicknamed the cheese grater. But all of those facades there, the main purpose of that is for the shading. So there's been some solar radiation modelling that's been done there, and that was the arrangement that was required to achieve that solar radiation. We've also got an in-house software that basically automatically works through various pile lengths, and it converges on the optimum foundation solution. So that obviously reduces the amount of material required for the foundations. It reduces the cost, and also makes it more sustainable. So trying to reduce the materials as much as possible and reduce that embodied carbon. When we're looking at specifying lower embodied carbon products, so for concrete, it's about the cement. The cement contributes to around about 60% of the embodied carbon of the concrete. And Portland cement, the traditional Portland cement, isn't great for the environment. So trying to replace that Portland cement with supplementary cementitious materials such as slag can actually help that. And also trying to change the mix design. So by reducing the water content, basically it's the water to cement content that gives it the strength. So by reducing the water content, we can reduce the cement content and achieve more sustainability. The only problem with that is that it can be harder to work with. Basically the slump reduces. So super plasticizers can be added to the concrete as well to make it increase the slump and make it easier to work with. For the steel, it's about the manufacturing process. There are companies that use scrap steel, recycled steel, and use an electric arc furnace can produce some green steel. And then some companies are actually taking it the next step further, where they're powering these electric arc processes with renewables. So they've got wind or solar farms that are powering these electric arc furnaces to produce really green steel. Timber is the most sustainable product that we have, although in some countries it's not readily available. So, for example, in Thailand, there are a few manufacturers, but a lot of the timber is also imported. And it's important that it's sourced from sustainably sourced suppliers. So, for example, chopping down an Amazon rainforest or something like that is not necessarily a sustainable supplier. So understanding exactly where that timber is coming from to begin with is very important. And then the earthworks, so it's all about trying to optimize the processes on site. So trying to optimize the cut and fill, trying to balance it out, trying to reduce the amount of double handling or having to take, cut off the site and then to transport it back to another site or back to the same site. Then if we look at a real project, so this is an office block, and there's two different options here for the floor system. The top right is basically a concrete slab that's supported on steel beams. It's what we'd call a composite slab. Down the bottom right is a PT slab supported on PT band beams. And the first step is to measure it. So by just looking at those images, we wouldn't know necessarily, unless we've had a bit of experience doing this, which one would be the most sustainable floor system. So we need to measure it. And so within Oricon, we have developed this internal software, and it automatically works with Revit. So it basically recognizes all of the structural members within the Revit model. You can easily add reinforcing contents to each of the members, and then it automatically does the life cycle assessment and informs what the embodied carbon is. It then takes it a next step further, whereby you can rotate around the 3D model in Revit and click on all the components, and it will say what the embodied carbon of each component is. So this is very powerful for what we're using it for at the moment in Oricon. And if we look at the results from using that tool on those two different floor systems, so on the left there is the concrete design, so the PT slab on PT band beams. In the center there is the steel design, so the concrete slab on steel beams, and then the comparison on the right. So this is the cradle to gate, so just the upfront, the A1 to A3 modules. And as you can see, it looks like the concrete's slightly less than the steel design. The colors there are breaking down for the different construction materials within the building. So the 40 MPa concrete, the post-tensioning, the 50 MPa concrete, the reinforcing steel, etc. And then the low and the high are basically the upper bound and lower bound based on different suppliers. So different concrete suppliers, different steel suppliers will have higher or lower embodied carbon associated with their products. So basically it's showing that the concrete is slightly less than the steel day one. Then if you consider the cradle to grave and beyond, the end of life benefits of the steel are greater than what they are for the concrete. Basically, the steel can be reused or recycled at the end of the life, but the concrete, you can grind it down and reuse the aggregate. But the end of life benefits, because they're so great for the steel, it actually pulls down. If we look at the comparison, all of a sudden the steel is slightly better than the concrete design. If we consider the whole of life of the project. So that's an interesting dilemma that we have in the industry at the moment. Should we be focusing just on today embodied carbon or the upfront embodied carbon, just considering construction, or should we be considering the whole of life of the project and also take into account those end of life benefits in 50 years' time? The other point about this is that steel manufacturing processes is expected to become more efficient over time. So the benefits that we're seeing today will potentially be less in the future. because it's more efficient. So this is within our business. We have the concept preliminary design stage. We have calculation, just spreadsheets to do very high level, just conceptual ideas. And this is great for understanding and steering the direction in the right direction right from the get-go, and providing just rough order of magnitude embodied carbon estimates and option studies to clients to allow them to make more informed decisions. Then during develop design and the detailed design, we have the real tool, which is what I was showing on the previous slides. So that stands for Revit Extraction Automated Lifecycle Assessment Tool. And then there's also commercial products available like One Click LCA, Garby, a few others that we have some licenses for as well within the business. And that can tie into the certification, particularly if we're looking to go for LEED or other certifications. Trees, for example, here in Thailand, we would be wanting to use those certified commoditized products like One Click or Garby. A few other examples here. So this is a Thailand project. It's got 100-meter long span steel trusses. It's supporting a big plantation on the roof. And we were able to achieve a 30% reduction in embodied carbon using recycled steel compared to the normal steel that was available. And then also the dual benefit of that is that at the end of the life of this project, when this asset is decommissioned, potentially that steel could be used on other projects as well.